Hello everybody, and warm welcome to this webinar. Today's webinar will be given on an ibaAnalyzer, an introduction it's called. And my name is Lars Olsson. I work as a team leader inside a group, Measure and Analyze, inside the Swedish company Begner Agenturer that represents IBA in Scandinavia. So just a few words. This is not meant to be let's say, training in ibaAnalyzer. It doesn't mean that this is something advanced. So you do not have to have any, let's say, pre-skills in ibaAnalyzer. So you could see this webinar as we try to keep it as a source of inspiration, let's say, for how you can use the ibaAnalyzer tool by giving a few examples here today. And my wish and purpose by giving this to you is that each and every one of you, every one of you will bring at least one idea from this webinar with you back to the factory and to try it or implement it, let's say, by modify it slightly and to learn something, to get an inspiration to work on, let's say. But first, most important, and I'm really happy to tell that we have participants from 7 different countries representing these 8 companies that I show now. So thank you already now for showing the interest in our products and systems by being here. It really means a lot. So thank you already now. Agenda for this webinar today is as follows. I will start to give some process introduction and background. It means I will explain just a few words about the actual process that I have chosen for the webinar, the process data we will work on. We then jump directly into ibaAnalyzer to have a look at some practical tips and tricks how you can do a few things. I will show you this step by step in the ibaAnalyzer. I will also show you how to extract data in an aggregated form and as segments into some kind of process database that you can have in your factory or just locally on your computer if you do some kind of investigations. We will then query data back from this database by the use of ibaAnalyzer, and I will show you how you can enable a very powerful drill down from an aggregated form of data. Maybe it's an average of a roll force or something, with the instant access back to the raw data, to the actual .dat file that created this average. And then we will sum up together just to try to, let's say, sum up what we did today with a few keywords and notes. And then we take a discussion. Process introduction. The IBA system, first of all, you already know about this, but we will just give you a brief overview how it works. There are some kind of signal sources in the system. In this photo, or there is this slide, it's in the south, let's say. Could be analog and digital signals, some bus monitors, PLCs, video signals, and information coming from manufacturing execution systems, and so on. We acquire those signals from the different sources into something we call the IBA PDA. It stands for Process Data Acquisition. Here it's the measurement itself is set up and defined, how fast we will acquire data and how fast we will, or with which sampling frequency we would like to store the data and in which data stores and so on. Everything regarding the measurement itself is set up here. We then store the data in 2 main formats. One is the .dat files, the other one is the HD server. And There are some differences between those, and I will come back to those in the next webinar actually. And for this webinar today, I will use .dot files as a signal source. We can read data into the analyzer, ibaAnalyzer, where we can perform our analysis. We could do long-term trends, reports, some alarm functions, and also we could, by the use of a database, we could also visualize data in our web interface, ibaDavis. There's also a south to north stream of data possible by using the broad connectivity of IBA to different signal sources. We can take in some signals from processes. Maybe we treat them a little bit, or we process them in the IBA PDA, and then we directly push them north up, let's say from like OPC UA or some other interface for other systems to use, like an MES system or something like that. We could also enable some alarming and analysis directly from the PDAs. So in the terms of process development and optimization, that goes in the width direction, let's say, of the screen, and machine connectivity or integration, we use the south to north direction. So in terms of the webinar map, we are now today here. We will cover the ibaAnalyzer, and we will use data that is stored by the PDA and to work on historical data. Next webinar in 2 weeks, we will focus on how to make automatic extractions to database, and also automatically update the visualization in ibaDavis on those data. And then we have 2 more webinars in mind. They are not planned by date, so we will come back to those later on. Some introduction to the process today. I have chosen a one-stand reversible cold rolling mill for strip rolling. And yeah, just a few words so we can, because we have to follow this when we do the example later on. We have an uncoiler on the right-hand side, some deflector roll and a thickness gauge measuring the thickness. Strip stand with 2 work rolls. The strip is coming out a little bit thinner, and because of the constant volume, you know, we have the strip is coming a little bit faster out than on the inside, so it's coming faster and thinner, and we can neglect about the width changes, so it's faster, higher speed, and thinner gauge. And then we recoil it again on this side. And then, when all strip is here, we reverse direction and we thread it this way over the deflector roll, or maybe flatness measurement roll. We put it in the thickness measurement and back into the roll bite, which is a little bit tighter. So the strip is coming out thinner and faster again, and we coil it from this on this side. And this we do back and forth till we are done. And the example today, we will have 5 passes through this mill stand. And the odd passes, they will go to the left, and even passes, they go to the right. And here are some examples of IBA data from a mill like this. This is a top view of a flatness measurement that you can represent by having all those segments in this roll in the width direction, and time on the x-axis, and then the flatness measurement, or actually the pressure measurement itself, is represented by the top view. This is a thickness deviation profile showing the deviation from the nominal thickness for pass 1, 2, 3, 4, and 5. And this is a speed profile, let's say, of the 5 different passes. But we will look closer to this, because what I will do today and show you the step-by-step inside the ibaAnalyzer is to compare the thickness deviation from pass number 1 with the pass number 5. And to do that, we have to prepare the data in some steps. And I will show you. You see, we have to stretch the data a little bit, and we have to transform the data from time to length, and we have to do a little other stuff to make it happen. And then we put the thickness deviation from pass 1 on top of the thickness deviation from pass 5. Okay. And now I will jump into the ibaAnalyzer. So the only signals available today are the 3. The thickness deviation from the left hand, gauge meter, or thickness meter, thickness gauge, and the right gauge, and the speed signal. Okay. So I will just start with this, the signal on the left-hand side from the thickness measurement. And then I would like to introduce some tools how to visualize things. We can call this, and normally I would say that I have a hard time doing this in Swedish, talking in a sentence at the same time I'm writing these commands in IBA. So I think now in German, in English, I think it will be even harder, but we try, and I think we'll be okay. But if I become silent, then you know why, because then I'm focusing on what I'm writing or typing. So now I would like to illustrate the deviation larger than 1.5 microns in this case, because you can see here the unit of these signals are microns. So then we go in and we use something called the X mark valid of the expression, and we would like to make the visualization for when the absolute value of that signal is greater than 1.5. Sorry for that. Great start. Always. But this will work. So what I just did, I just marked in the curve, please show me every single measurement point that is larger than the deviation 1.5 microns. So then you can have an illustration on your thickness curves. Let's say visually how much is outside the given tolerance. In this case, I just had 1.5 microns as an example. Now I will use something called upper envelope. Then we use, I will show you soon why this is a good, we use the same signal followed by a time interval. Okay, upper envelope, and then I will duplicate this to create a lower one. And this normally I used a lot we use a lot to illustrate, let's say, process windows, or yeah, because in this in this corridor, in this area, the process normally runs or performs. It gives you an idea about boundaries for the process where you can detect deviations or process variations. So what I mean, if you take this left hand or you put it in the middle here, they will be, okay, maybe I will increase the thickness of the lines a little bit, like that. So it means that you will see somehow a normal performance. If you do this over and over again for every new strip, then you can react if you have a lot of points outside, let's say, or you just leave it like this. Okay. Then I would like to show you another signal that is you can make averages on the values by the use of a valid condition. It's called average valid, or thickness signal again, or thickness deviation actually. Now I have to put in a expression when this signal is valid. So in this case I choose O:8, which means the speed, and I put it when the speed is greater than 300 meters per minute in this case. And it calculates the different averages for the thickness deviations when the strip speed is greater than 300 meters per minute. So if I put it, maybe here, you can put it here actually, and then we have another color maybe. We take something green and we make it thicker. So if we have a very close zoom here, I think you will see that they a little bit. So these are the different the averages inside for each strip for each pass. Sorry, when the strip speed is greater than 300 meters per minute. So if we look at the speed profile, this is the speed for each and every pass. And what we can do now, since we do not have any length signal here, we can duplicate the speed signal and just call it length. And then we will integrate. Oops, sorry, I'm on. We will integrate the strip speed, and then you have to remember that you have to divide it by 60 here because it's meter per minute, so we need the meter per second. And now I will just integrate it like this, and you see this is not the length, so we have to reset the integrator on some kind of signal, and those we have to create in this case. I will show you now how it's done. We will start by adding something called a pass sequence. And the pass sequence we can define as the strip speed, again, maybe greater than 1 meters per minute or something like that. I'm just for the example. Well, then we can count, let's say, just for you to see. Duplicate this, we call it count passes. Then we can count pass sequence like this, and you will have some stairs. Maybe I put it like this, it's easier to see. You will have some stairs. We put it actually on the speed profile itself. Not the same scale, it will be hard to see, and then we scale it on different colors. Okay, so pass number 1, 2, 3, 4, and 5. And why did we do this pass sequence? Yes, because we needed to reset the integrator somehow. We need to zero the speed, the integrator per pass, to have it calculate the actual strip length instead. So now we just use to we reset this by the use of pass sequence. Oh, like that. So this means integrate the speed signal divided by 60 to have it meters per second, and please reset this integrator each time the pass sequence is 0 to take down this again. So this actually now, you see 1,000 meters, maybe some 1,500 meters, 2,000 meters, and so on, is the actual length per pass, strip length per pass. So now you can see the strip is getting longer, as I told you in the PowerPoint slide, and yeah, it's also illustrated here. Let's say we put it like this, and we see like colors. So if you would like to calculate the maximum maximum length of the strip length, you can strip length per pass. You will just use something called max valid of the signal rolled length of the length, and we make it valid on the pass sequence. And yeah, I put it on a polygon so you see, okay, like that. So here is the actual values, the max values. Okay. Now we'll minimize this a little bit. Now we have to put in an indicator for the pass number 1. I will now focus and closing in a little bit on the example I told you about, putting thickness deviation number 1 on top of the thickness deviation from pass 5. So we do something we call a indicator for pass number 5. It will be when this pass sequence is true and the number, the actual pass number is 5, and then we duplicate this, take it to pass number 1 we need, so it's when the pass sequence is true and the count passes equals 1. So now we have two signals showing for pass 1 and pass 5. We can choose the colors like that, and now we need to cut out some thickness values from the first pass and from the 5th pass to start with. So we create something called thickness pass 1 cutout, and we use something called xcut valid to do this. It's called xcut valid, and we will cut out from the signal number O:0 for pass number 1 Okay, and then we duplicate this and do the same again for pass number 5, and I will soon show you why. So we take the same signal, but when pass number 5 is running, let's say. I will minimize some more here so it's easier for you to follow. Then we need to do the same for the speed signals. We take a speed, pass 1, cutout. So we use actually this again. We put in here and we just change this to the speed. And sorry if this is a little bit fast because I see I have to speed up just a little bit. We cut out from pass number 5 also the speed. Okay, and now we will transform these values that are time-based into meters. So we use something like this one. We duplicate, we add a signal here. Thickness, pass 1, cut out on the length-based version. We call it, we use the command time to length of thickness pass 1 cutout, and we need to put in a speed signal for that actual pass. And see what I did. I forgot to divide it by 60, as I told you. Now the thickness, sorry for being a little bit, the thickness curve, the deviation from pass number 1 in seconds here, are now transformed to be displayed as a function of the actual strip length from pass number 1. That's the purpose. And I do it also for, as you can imagine, you see the pattern. We duplicate this signal, we change this to pass number 5, and we change also this to pass number 5 and 5, and we execute that one. And now you see that those are different lengths, exactly as we expected. And now the only thing that remains to be able to compare those is to add a signal that we will actually use this signal from pass number 1, and we put the name because what we will do now, we will use a command that is called x stretch, and you will soon see what it does. It will stretch the thickness, the length-based thickness from pass number 5 to match or to fit the length of the length-based thickness from pass number 5. At least that's the ID. Okay, so we will minimize, we will slow down a little bit now, just to. So what we have done now, we have transformed 2 different signals on time to the length-based versions, and we have stretched one of those, the one from pass number 1, to fit the length of the 5th pass. And then you can put them on top of each other and maybe change the color a little bit of the first pass. We can also increase the thickness. So here now is the overlay of pass number 1 on pass number 5, and then you can maybe directly see some correlations that we had some errors or deviations from pass 1 that can be visible in pass number 5 already. I will now jump into, or actually I would like, we do it one more because this you have to see if you haven't seen it. We call it just length marker. And I will write something here now. Base. Then we can see the idea of it at least. And we will transform again from time to length. I just show this very quickly because we are running a little bit. So now sorry for being silent. I'm focusing on right typing, and then instead of this number we will put in length marker. Okay, now just to show quickly here. Sorry, here. Now here, when I move the cursor here in the pass number, oh, actually we can do it here. We put it in this. It's easier to see for you. Now to summarize, I move the time cursor over here in the 5th pass, and I will directly see on this label where this correlates to in the length-based version. So here I find something strange in this area, then you can see it's 3,200 meters inside the strip. Okay, now I do a quick change to already prepared .dat file. It looks more or less exactly as what we did, some other colors. Just to show you the data extractor very fast, and how this is done in detail we can come back to later. I can read out some information from the info field inside the .dat file. Here I take only the coil number and some production start. I have some computed columns. Just as an example, standard deviation of the different thicknesses from the different passes on the left-hand side. And I also calculated some reduction pass for each pass. Okay, and it will. So now I will show you this table here. It's empty. It's nothing inside but the columns that are already prepared by the standard tools from here. And we do the extraction now, and we move back a little bit fast, I'm sorry, but here. Now the actual data is read in and extracted to this column. So here you can see, in this case, coil number something, very old strip from 2009 something, the different standard deviations and the reductions, 27%, 28%, 28%, and so on. So this is just an example how you can extract aggregates from a .dat file, let's say, into a database. And to illustrate this even more, I will now change to another example that looks like this. Just two signals again. Some process signal, the blue one, and the red one now is, let's say, the valid function for when we would like to extract data. So it means, if you zoom in here, it means that for each and every case of the red occurrences, we will extract data from this signal. And this I have already done, but I will now show you how you can read back the data by an SQL query. And the first thing is to have it as a signal. So now I put in, let's say, the average value. Okay, it shows in green. That's okay. We just make points of them. I will increase the size a little bit, or as much as possible, and then we zoom in to have a look what happened. Here, what can we choose? Maybe here. So now the green dot here represents the average value of the blue line during the duration of the red signal. So this means instead of all the high resolution data, we extracted just one single value that means something for this occurrence. This could be done for, let's say, if you are interested in knowing the average roll force in the head in pass number 5 for the last 8,000 strips you have rolled, you can just do this operation and have them presented as an average if that is meaningful for you. And now I would like to go back and show you how it can be also related to with the drill down. We place it in the overview tab that is down here. Instead of having them as signals, you can you can uncheck a little bit here. See, now you see the process value on the average in the overview tab instead of a signal here, and you can move this cursor X number 1, the marker, and what we can do is actually you can go in here on some interesting part and you double click this, and now here is visible the dots, only the dots now that are used to calculate the green value, let's say the average value during this duration. So what does this mean? Yes, it means that you can actually find, if you find something interesting, here's another case. This maximum value over here. This looks strange. If this is a trend for some process parameter you are following, and then you find something like this, you are immediately interested in knowing why. And by double clicking this little red diamond here, you can, or dot here, you can go to visualize what is actually being used to calculate that value. And that is a very strong feature. So have the instant drill down to the raw data available from an aggregated value. Okay, and I will sum up just another example for you. I showed you some kind of top view representation of a flatness measurement roll, and again here's my, you see I like this because I when I move now inside the strip here, I will directly see where it is in the length marker, but this I've already showed you, so I can take that away just to focus on how you do this if you do not know. It's a very powerful tool to visualize data. It can be, like I said, it could be like a flatness measurement from a cold strip mill. It can also be heat or temperature measurement. We can use it for a strip profile. You can use it for indicating temperatures inside furnaces zones, whatever. You create something called a logical expression, and you just assign the dimension of this vector that will be used, and you assign each of those zones to a value, and then you can visualize it as a top view or some 3D plots and stuff like that if you're interested. A very powerful and simple way to visualize data, I think. And now back to the not so interesting maybe, but we need to sum up PowerPoint. I like to sum up by giving you some notes and keywords, what I have done, what I have showed at least. So we use something called time to length. It actually translated the time-based signals to length-based signals. You remember we took the thickness deviation from pass 1 and 5 and made them and plotted them as a function of the strip length from pass 1 and 5. Convert base, that's what I did when I used for the marker, you know, when the marker is slided accordingly to the time cursor, it slided automatically and showed where in the length-based data is this position. Convert base. X stretch I used to stretch the signal from pass 1 to fit pass 5. X mirror, actually, I didn't use that because, but I would like to mention it because this is how you take care of even passes. Because then you know what's happening in the head of the strip in pass 1 will be in the tail of the strip in pass 2. So if you compare an odd pass with an even pass number, then you have to do the same operation as I did actually, and then you follow it up by a mirror. And it does exactly what it sounds like. It just mirrors the signal. So the head will become the tail and vice versa. X cut valid, we cut away stuff that is not valid in a signal. I used it for oh, sorry, I forgot what I used it for. I cut it. I cut away pass 2, 3, 4, and 5 to just keep the values from pass 1 as an example. X mark valid does more or less the same as X cut, but it leaves the data, but it just marks what is valid. And max valid I used to take out the maximum length per strip. Per pass, sorry, I took out the maximum strip length per pass. Average valid, I used to calculate an average of the thickness deviation when the speed was greater than 300 meters per minute, I remember. And envelope, you remember, it was the first example I did to show the process window, what is normally where you can actually use to stack data as an overlay on an envelope to start to see trends, or if you are performing better or worse, let's say, what you're used to. The multi-dimension logical expression is used for sorry, this is in Swedish. Planhet. Now you learn something in Swedish as well. Planhet means flatness in this case. Okay, you see. Yeah. Anyhow, this is we used it to represent data from a flatness measurement roll in a 2D top view actually, where I assigned different signals to different zones, let's say, or columns in this vector that we created by the use of logical expression. X marker 1, it's a command to use to take data from where the first marker is positioned. The integrator I used to create, I created a length signal out of a speed signal. And I put here also the differentiator. It does the opposite if you exactly as you're used to from the school, let's say. It will you can go from if you have a length signal available and you would like to know something about the speed, you can use the time differentiate of that signals to have the speed. We use some logical operations, operands, to take care of some expressions. We counted the different passes. ibaAnalyzer is a software. The data extractor was a tool, let's say, to use to extract data to the database, and then we read it back by the let's say the import functions of the data extractor when I read the data back from the database. Single words, just some words on as a final to sum up. We are now in the green box here, talking about ibaAnalyzer, talking about post-processing data. Next week is, in 2 weeks, the 11th of June, we will take care of doing what we actually did today. I did one extraction manually into the database. Next time I will show you how to use the iba.coordinator coordinator to make that happen for every case that you define. We will use 2 cases then. I will show you in terms of a central database, let's say, that serve all your users in the company with data that is interesting, and you would like to have all this happening automatically with the latest available data. And I will also show you as a local example, maybe carried out by the process development engineer that investigates something in the rolling mill or in the bakery or whatever your process is, that you can extract data locally on a database on your computer to just investigate things. And I will show you how it works. And I will also send some notices by email on different events when we extract data to this system database. Maybe someone would like to know about this also. It could be some error that you are tracking that suddenly happens. And when this happens, we extract some key data for that occurrence, and it's also sent emails to some people about now it's happening, let's say. I will show you how you do that. And yeah, I think that is more or less, yeah, okay, as I said, the 11th of June is the next time. And 3 minutes. 3 minutes too long this time. I think it's related to the English skills of myself a little bit. And if you would like to learn more about how exactly we did things here in this webinar, or some other discussions, or you need some education inside other areas of the EBA system, please have a look inside our webpage, what we can offer you, and nowadays also online trainings. All right, then I thank you very much for your for participating in this presentation, this webinar. I hope it could give some inspiration for you to try, or at least some new ideas. And please do not hesitate to come back to us with your questions, and if you have any or ideas, we are ready to help you, and looking forward to meeting you again after this virus period, let's say. Okay, stay safe, stay healthy, and take care, and we talk again in 2 weeks. Thank you very much.